Okay, let's get started. Today we're happy to have Carlos from Princeton telling us about some new directions in direct detection.
Yeah, so thanks for having me here. Really excited to talk about this. It's been a trilogy of studies in this vein, and so I think we're getting very close to putting the capstone on this. And so really the point that I want to make today is that there's very interesting science to be done with molecular mesoscopic systems, and I'll try to define very clearly what I mean by mesoscopic in a second. But first, let me define what the problem is, right? We want to try to detect the interactions of dark matter with some electronic system that starts in some initial state psi I and goes to some final state psi f, picking up some momentum q, and for sub-GeV dark matter of order of MeV, the energy accessible to these transitions is of order of EV. So we can ask, what has transition energies of this order? Well, we see that atomic ionizations sort of lie close to about 100 EV, and the visible spectrum is really where we want to be to look for sub-GeV dark matter. In fact, the reason why it's visible is because most things that have compounds and molecules in them are active at these energies. This is also where most of benchtop chemistry takes place, and so there's already techniques that have been developed to predict the behavior of these electronic systems very well. As a first pass, as a first proof of concept, one thing that we did was select a target called Algin 301, which is just a benzene ring with two methyl groups at the end of it. And the electronic system that we're interested in is the electrons that flow in that ring, right? And the reason why we picked this is because this is a readily available scintillator, and it's very easy to construct a model of what these electrons are doing. So we begin with a very basic linear combination of atomic orbitals, where we say, okay, at each carbon in the ring that we're interested in, we're going to drop an atomic orbital, and we're going to let these things just have nearest neighbor interactions, and we diagonalize the Hamiltonian. That's very easy to do. We obtain what are called the Huckel molecular orbitals, and we perturb them and allow them to mix through this electronic repulsion term. And what this does is it gives us a totally symmetric ground state, which is what we expect, and then some singlet excitations above that. Okay. The reason why we do this exercise is because computing things with these orbitals becomes an exercise in the Fourier transform, and that's very nice for everybody. So we think we understand what the electrons are doing in this very simple Zion system, and what we're going to look for is the emission after some primary excitation. So this is a diagram of what the excitation to a dark matter collision is going to look like. An initial absorption of energy from the S0 ground state to some excited singlet state, followed by a very rapid non-radiative transition down to the ground vibrational state of S1, and then a radiative de-excitation. Okay, we're trying to find those radiative emissions of single photon events in our scintillator. And this was a proposal that occurred in 2019, and very quickly we put together a proposal for an experiment, and the experiment was extremely simple. You take a vat, put xylene in it, you cap it off with a PMT, and you observe in blind and active mode. You try to compare the rates of some actively exposed detector versus just what the limiting rate of the dark rate of the PMT is.
But what would be an example of an active exposure?
Oh, that just means that the PMT is actually looking at the scintillator, right? So you're measuring the one photon events versus just.
But it's not like you have some external.
No, it's just so you can make
It's
a difference.
whatever stuff is out there is exciting it.
Right.
Which might be dark matter.
Yeah, that's the hope.
No, but it could also be other stuff.
Yeah, so that's exactly why you blind the thing afterwards, is that you know that whatever you're observing is at least coming from your scintillator and not from your photodetector.
Maybe what I should ask it differently is, so people do these experiments where like they have a source of some transition in some nucleus that produces a photon of some known energy, that sort of stuff. It seems like you could do that too.
Oh, you can absolutely do that.
And so have you tested that your theory correctly?
Yeah, so
describes it?
to calibrate the actual scintillator, the experiment that you do is called electron energy loss spectroscopy that measures the probability of the internal transitions. And we found that did match the experimental results. The blind versus active is just to characterize the PMT and the limiting rate there. And so this experiment was deployed almost immediately. So this is what that looks like. This paint can looking thing is a totally internally reflective cryogenic vat of 1.5 kilograms of L-301. A nice big PMT that comes on top. Right now we're blinding it in this picture, and this all gets put into a big barrel of wet bricks with neon vetoes above and below, and we take data, and it turns out that because we're looking for rates that are of order hertz, you only need to take data for about a month. And we did that, and this is the proof of concept. So here are the sensitivity curves for this experiment. And on the left-hand side, we have something akin to a heavy mediator. On the right-hand side is a light mediator, and the dotted L-301 line is what was actually measured, right? So after 2 months and sort of the simplest thing you can put together in essentially a scientific garage, you're already within striking distance of cutting-edge experiments. The black line is where we would expect the sensitivity of the experiment to be if we had sort of bleeding-edge top-of-the-line PMTs, right? And so that tells us that we're really just limited in this setup by the dark rate of the PMT. Okay, so this was a very nice proof of concept that organic scintillators really do very well. And that proves something that we knew theoretically, which is pound for pound, L-301 does as good, if not better, than silicon, above about 10 MeV. So this would be the sensitivity for 1 kilogram a year exposure, and he had 0 backgrounds. Right? So this was telling, and the proof of concept, I think, was really encouraging. And so we wanted to think deeper along these lines. And we wanted to select a next molecule to really take advantage of molecular systems. And so
what goes into that set of us? What are the assumptions here?
No backgrounds, just what are the possible visible rates that you would expect for a kilogram of silicon. So here just producing 1 charge carrier pair versus L-301 of a single photon to the first excited state. Right. So that, I mean, there's nothing deep about this. This is just calculating the transition rates. So moving forward, we chose a more interesting molecule, Trans-stilbene, which is very similar to the xylene. You have these 2 rings that are connected by this ethylene bridge, and so the electrons are allowed to flow anywhere on that network. It also has some very interesting characteristics in that it lies in a very organized crystal structure. So now you can deploy this in the solid state. The first excitation energy is lower than xylene by about 20%. And that first transition is dipole allowed, whereas in xylene, it was classically forbidden. So you expect that your rate is going to be even higher. But also, and I think more importantly, is experimentally, you can find and you can produce very pure single crystals of Trans-stilbene that are macroscopic. I mean, we're talking about, kilogram scale single crystals of Trans-stilbene have been produced for more than a decade now. And the idea is still the same, right? You have a vat of these molecules, and you're going to excite one of them, and it's going to emit a photon. And what you want to know is, what's the likelihood of picking up that photon once it leaves? Because now you're in a condensed matter system. And so that probability is proportional to this AXX, which is the overlap between the absorption and the emission, right? When we calculate this and measure this in the lab, turns out for solid Trans-stilbene, it's, order 1, 65%, right? Anytime you excite any molecule in your crystal, even if it's a macroscopic crystal, you'll get that photon out 65% of the time. And that's at any energy, right? For any excitation energy. That's pretty unique for molecular systems. Semiconductors suffer severely at low energies. Okay, so now we want to calculate the rate for this Trans-stilbene. And so here is what that calculation involves. And so we know we've characterized the PMT efficiency, we know the full quantum efficiency, and the inside of this integral, without getting too far into the weeds, really factorizes into 3 pieces. This eta, which tells us about the velocity distribution of the dark matter, F sub dm, which is the form factor of the dark matter, which parametrizes the momentum dependence of the interaction between the dark matter and in our system. And these little Fi's, which are the molecular form factors, and they just parameterize the probability of making that excitation and picking up some momentum Q. Okay, so first let's discuss the thing that's really the most important thing, which is the velocity distribution. We take the simplest thing, just a purely isotropic standard halo model. And to that, we add the motion of the Earth, right? So we add the preferential direction that's slowly rotating throughout the day. That's parameterized by this bar theta parameter. And beta here is the alignment of the principal axis of the crystal with respect to the zenith. So throughout the day, the crystal sort of sweeps an angle as you're going through the dark matter wind. And what we're trying to find out is, as this crystal changes orientation, how does the rate change throughout the day? Okay. And that all depends on the molecular form factor, right? So that molecular form factor, there's no reason to believe that that's an isotropic thing, right? For a liquid, you sort of directionally average everything because this is a totally disorganized system. But now you have a crystal, and the crystal is pretty well organized. And so we want to know how to put that together. And if we want to do that, then we need to calculate that form factor a little bit more precisely than we did for algebra 301. And to do that, we need to let those singlet states mix, right? And they mix because of configurational interactions. It turns out for Trans-stilbene, this is kind of a pain to do, but it's doable. And so these configurational interactions, what they tell you is how each singlet state is going to mix with one another. And this all seems like I'm spinning plates, but the reason why we do it this way and not with DFT is because once we have the states written as linear combinations of these configurations, the inner products of this single body operator, which is the scattering operator, really just boils down to linear combinations of single particle inner products. And so that's really nice. That can be computed on any laptop. Okay, good. So we put this together, and this is what those form factors look like. So this is a slice of the form factor along the plane of the molecule in the space of Qx and Qy. So on the left-hand side, we have two plots, which are the form factors for the first excitation. On the left for a heavy mediator, on the right for a light mediator, and a couple of things should stick out. One is that this thing obeys the same molecular symmetries that the molecule does in real space, and that follows the intuition that we should have from condensed matter, right? This is something akin to the reciprocal space. Another thing that should stick out is that there's really two scales here, right? The outer ring corresponds to the small benzene rings on the edges of the molecule. And the two peaks correspond to the fact that their scale their structure at a larger scale, which is these two rings separated by some distance. So it's very intuitive to know where these peaks come from. And what happens when you multiply everything by 1 over q squared is that this inner structure in reciprocal space gets over accentuated. And that'll be important in a little bit. The right two plots of the molecular form factors for the third and fourth transition. The second one is forbidden. Okay, so now we know how to compute this, and we're gonna sort of put everything together and ask the question, what's the rate throughout the day? And so this is the daily modulation as you would find it in a 24-hour period. To our knowledge, these are the biggest proposed daily modulation amplitudes for any target. And so what this is on these two top panels is heavy mediator on top, light mediator on bottom, for two different orientations of the crystal at t = 0. When the mass of the dark matter is very light, right, the amplitude is at its biggest, right, because you're really just exploiting the fact that you're near threshold and whether you're able to overcome the threshold in one preferential direction versus the other. And so we understand that fairly well. But the natural question that arises is why, as the masses go up, does the amplitude not go exactly to 0, as you would see in silicon or any other semiconductor? In fact, for a light mediator, we find that amplitude remains as large as 25%, even at arbitrarily high masses. Right? That is an impossible signal to fake in the laboratory. Right, that would be observing a scintillator glow and dim throughout the day by, an order one amount. So we wanted to know really how to explain this behavior. And so these are those same form factors that I showed you before in two different cross sections. So on top, taken in slices in the plane of the molecule, and then on bottom, looking at the molecule sort of edge on. And what these kidney bean shapes are the kinetically allowed regions for the dark matter scattering, right? So they all sort of start roughly at the same place, depending on how you orient the crystal. And throughout the day, these four kidney bean shapes, which correspond to the four orientations of the crystal, they dephase and orbit around the origin. And as they do, they go, above the peaks and through the valleys, and that's what generates the amplitude at these low masses, right? And both in plane and sort of face on, you see that the modulation is controlled by that behavior.
On the previous slide, it said that it's not highly dependent on the orientation of the crystal, but you mean the amplitude of the modulation, but the phase would still be dependent on
Yes.
it, right?
Yeah, the amplitude is not dependent, phase totally is.
So you could have like multiple crystals oriented differently,
Mhm.
see the modulation with different phases.
Yeah, so this is one of the things that we're really pushing for is in these designs where you have your target separate from your photodetector, you can swap out whatever crystal or whatever orientation of the crystal you want, right? In fact, if you were able to have really good control over the orientation of the crystal, you could have it always pointing either into or, away from the dark matter. Right? That would be a very difficult signal to use.
Hello? There's a question I've asked you before, but so in the previous slide, you showed the modulation is sizable even for very large masses.
Yeah.
So the standard intuition is that at low masses, when the energy transfer is close to the binding energy, that's where you get most of the modulation.
Yeah.
But now it seems to be that you get very large modulation, even when the recoil energy is super large.
Good.
So
We're
what's
about to
wrong
get
with
there.
my intuition? Yeah.
Yeah, so that's the very next slide. At higher masses, those kidney bean shapes grow to encompass the whole plane, except for a kinematically forbidden region, right, of where Q min is still non-zero. And throughout the day, those circles still make small orbits around the origin, right? So the outer structure doesn't matter anymore. You're always sort of picking that up because that's always kinematically allowed. But the inner structure that corresponds to the large scale structure of the molecule, that goes through these walls of kinematically forbidden territory, and that's what drives the modulation even at high masses.
And what's making the inner region kinematically forbidden?
So that's just Q min, right? Like when you calculate what Q min is for the velocity distribution of dark matter to drive any energetic transition, you find that there are regions that are kinematically disordered. It's the minimum momentum that you need to drive delta E. And so our intuition would lead us to believe that if these inner features were over accentuated, for example, by a light mediator, that would have the highest modulation amplitude, and that's exactly what we see. Right. This is why the light mediator case has modulation amplitudes of 25% at any mass, at least. So we think we know exactly what, where these amplitudes are coming from. And the fact that we can trace this back to the structure of the molecule means that perhaps in the future, we can really think very deeply about how to select the ideal molecule to suit a particular dark matter form factor. In other words, we would like to get to the point where we could engineer a wave function to give us the amplitudes we need. Okay, so let's put that together and ask, what does this mean for our sensitivity? So these are sensitivity curves, again, for heavy and light mediators. And the thing to focus on is that there's two different sensitivities, right? One is the discovery potential, because now you're looking for a pretty unmistakable signature. And that's the yellow line, right? So this is for a 1 kilogram your exposure and for a background rate of like 1 per minute, which is, we think, doable for commercially available PMTs. And then the black line is if you saw no modulation whatsoever, right? So that's just an exclusion. And what we find is that even for this 1 kilogram year proposal, you can start dipping down into, benchmark scalar freeze out or freezing scenarios. And because you're looking for this modulating signal, this sensitivity curve scales linearly with exposure mass, right? So even though at 1 kilogram, you're really just starting to press on these benchmark models, by the time you get to 100 kilograms, which is again, quite inexpensive for something that is essentially lighter fluid, you're really, making some headway to excluding, 2 orders of magnitude in mass in some benchmark models. Okay, so do we have any questions on this?
Quick question.
Yeah.
I haven't thought about this ever really that carefully, but how much does like a daily modulation help you in just overall terms of like sensitivity? Like let's say, like does it actually help your analysis in a parametric way? Like let's say you're looking for something that's oscillating and your background is not necessarily something that's oscillating, but it's just like some random noise. I would imagine it could have a component like in Fourier space at that frequency. So I'm just wondering like how much, let's say you don't see anything, but you build into your analysis in the smartest possible way to say, I'm looking for an oscillating signal. Does it parametrically help you? Like how big of a deal is it?
It does. It does. So let me find the right line to point you to. Yeah, so I don't think this is the right plot to show it to you, but at the end of the day, it's exactly right. You're looking for a signal that modulates, which means that in trying to calculate what your background ought to be, you can disregard anything that's steady state. And
Is that really true? Because I would have thought it's like some Gaussian random noise, which is like, I'm thinking kind of like axion experiments is where my intuition is coming from.
no, but
There
yeah,
you're looking for an oscillating signal. Your noise isn't oscillating, but it has, if you do like a Fourier like series, it would have power in like a,
But you should sort of like
Cut all
square root of
frequencies.
days that down or something.
you would what?
Square root of days that down.
Yeah, okay,
Right over enough days, you should.
sure. Okay.
no, but I mean, you're right. It just means that you're
Noise,
looking at
yeah.
in a band in Fourier space instead of just looking at
Right.
this completely steady state.
Okay.
And so we're trying to answer that question right now of doing the statistics very, very carefully and seeing how to treat backgrounds that are Gaussian backgrounds.
Right.
But the answer is like, yes, it does. help.
Okay. I
We
guess
want to quantify exactly how much it is.
right. So like an axion, like in like typical ways, it grows like square root of integration time or something like that. I guess in this would be something similar.
Something you think.
Okay.
Although it's of course always bad if the background is really huge. I was going to ask you, what is the background? Do you know?
Good. I was hoping somebody would ask that. So the backgrounds actually turned out to be not that many. So the main thing is muons. We considered a couple of things, and the
Nothing
thing,
very new ones. So going deep would be good.
yeah. So the last experiment we did was just 3 meters underground, and we put in a proposal to get some Fermi space that's deep underground. And we're hoping to do much better. But it was sort of suggested that we should be careful with radioactive backgrounds. And the thing to keep in mind is that there is no radioactive decay that can occur inside the scintillator that would only put out a single photon. Right? If anything decays inside the scintillator, it'll light everything up. And so that's just not a fact. We see the very, very tail end of beta decay, but even that is just so suppressed. So really the only thing is sometimes muon. But this is kind of naturally background free, especially the oscillation. And if you want to do even better, say you run this experiment, you observe something, and you say, well, maybe we can't characterize the backgrounds very well, you just swap out the molecule. And that will, change the phase and the structure of your signal significantly.
Well, this feature that Neil pointed to, that you can orient them different ways, and then the modulation should be very
Yeah.
predictable, what the relation is between the different orientations.
Yeah, that's right.
I mean, it'd be crazy to have like one at a minimum and one at a maximum at the same time.
Yeah, totally. And
That would
then
be-
turn them sideways and
yeah.
they don't.
Yeah.
That would be very, very, very hard to fake.
And just deploying them at different places on Earth also makes a difference. Because it sweeps out a different solid angle. But yeah.
So can I ask, like, physically, why you're getting daily modulations even for large M-chi? It's because you have some scale in your molecule that's comparable to Q-min.
Yes,
Is that right?
Yes.
Like if it's because of that, that like when the like your kidney beans move around, you can actually get like significant changes.
yeah. Really, it's almost by serendipity that the, 1 over the largest size of the molecule is Q-min for our velocity distribution.
I see. So you would want to pick molecules that have this kind of.
Exactly,
Okay. I see.
exactly. And, they exist, dime a dozen. Okay, so what if we want to do better? Well, if you want to do better and you want to start driving towards lower masses, then you need to really start lowering the threshold. The energy threshold for Trans-stilbene is 5 eV, and we want to do much better than that. So if you want to get down to 1 eV, then you need to have a box for your electrons to sit in that's micro to nano scale, right? So like hundreds to thousands of atoms big. And luckily these things exist. And this is what I'm calling mesoscale, right? When you've reached a large molecular limit and you're saying these are now macroscopically extended objects that behave like macroscopic quantum systems. And they have transition energies that sort of live in the infrared, right? So we're just continuing to go down this scale. What is a quantum dot? Quantum dot is just a nanoscopic semiconducting sphere, right? So you can generate these in a laboratory pretty readily, and the way that that they differ from a bulk semiconductor is really only at the band edges, right? So what's going on is that the electronic states near the band edges behave as if they were ideal particles in a box, right? So the energy of confinement, for example, which is the energy of what the electrons see on long wavelengths, is just the particle in a sphere solution. They also have interactions, so that's the exciton energy that serves to stabilize these states. And so the total energy of creating these particle pairs in these semiconductors just becomes the band gap, and that is modified by the confinement energy and the exciton energy. Now, depending on the size of this, you can actually get rid of the exciton energy, which is by making the quantum dot sufficiently small. The Bohr radius of this exciton is much larger than the radius of the quantum dot, and then you're really just modifying the band gap by a particle in a box state, right? So for all intents and purposes, the band edge is replaced by single particle states. Okay, this is sort of what that looks like. It's just a nanocrystal, usually covered by some stabilizing ligand. And the reason why you do that is to be able to pull them into a suspension, usually of alcohol. And the characteristic radii here, of order 5 to 10 nanometers. And the reason why we chose these sorts of things is because they behave essentially as if they were man-made molecules. Okay, and so this is sort of the proof of that. On the right-hand side, you have the absorption and emission spectra for a really standard organic scintillator, right? So we have peak terphenol here, which is very similar to the Trans-stilbene we just discussed. And the salient features to keep in mind here is that the solid line, which is the absorption characteristic, goes to zero very quickly at low energies. That just means that there's a gap that you need to overcome. And it sort of rises arbitrarily at high energies. It can absorb pretty much any energy above that before you ionize it. But once it absorbs that, it only emits in a small band, which means that all the extra energy very quickly gets rearranged, and you always emit a photon roughly in the same band. We want to know if quantum dots behave the same way. So if we look at those characteristics for quantum dots, we find the same thing, right? A compact emission band and an absorption band, which has a gap peak and goes to arbitrarily high absorptions at high energies. And so these things have been treated for quite some time as if they were just man-made molecules, where the knob that you can tune is the radius, and that allows you to engineer the wave function. What's more is that private industry has really embraced quantum dots, and so these things have become extremely scalable and cheap. Here, for example, are zinc cadmium selenide quantum dots, and really, depending on the time of your reaction in solution and the concentration of the reactants, you can pretty much select radii that are monochromic in even in the visible spectrum. And so we think that these can be generated all the way in the IR with the same sort of selectivity. What's more is that their bulk quantum yield for photoluminescence, right? The probability that you'll get that signal out of a bulk is quite high. It remains at like, 24%, even at pretty significant concentrations. And if you wanted to deposit these into solids, you can. You can load them at like 60% mass massive scintillator into plastic matrices. Okay, so the game is the same. It really comes down to calculating now the molecular form factor for these man-made molecules. And I'll try to build up the intuition for how one goes about it. Right, so I'll do that by comparison to bulk semiconductor, right? In the bulk semiconductor, the electrons live in these Bloch states, right? Which are really a long wavelength plane wave multiplied by a Bloch function, which knows about the very small microphysics and the local symmetries of the lattice. In the quantum dot, the microphysics behaves the same. It's still the same crystal lattice, but now the long wavelength solution changes to be essentially a particle in a box. And so that tells us a couple of things. One, we should expect that at high energies and high imparted momentum, these two systems should behave exactly the same. And this also tells us that at very low momentum, only the edge of the band gap should change. Right? And it turns out there's good experimental evidence for this. So this is on the left-hand side is the density of states for quantum dots of lead sulfide. And we see that when these clusters are very small, right, when there are only 8 atoms, the density of states are just these peaks, these single particle peaks. But very quickly, once we get to the 100 atom state, you're really starting to populate the continuum of the density of states, right? Where really the quantum nature, the quantum confinement effect is just there at the very edge of the band gap. That's great news. That means that we can make some assumptions in our underlying model, and this is something that we did with Warren and friends, and we put together a model that takes into account just the changes to the band edge of a semiconductor, and asked how does the sensitivity, the projected sensitivity for a semiconductor change if you manipulate this band edge, and that's what's on the right. And what we see is that it doesn't change it. So we have here 2 bulk semiconductors, germanium and silicon, and superimposed a silicon quantum dot of radius 5.6 nanometers. And we find that really, as long as you're even a little bit above threshold, these 2 lines are right on top of one another. Okay. And really, this is our main takeaway from this whole study, is that if you have a mass of semiconductor, the number of charge carrier pairs that you can generate with a dark matter interaction should be the same if that mass is monolithic, like in Sensei, or if you take that mass and disperse it into quantum dots, right? And that seems very intuitive when you say it that way, but it's actually not a trivial result. And so what this means is that as long as you have a good way of calculating the bulk, you can calculate the interaction between dark matter and quantum dots very, very well. And this is sort of our preliminary sensitivity curve. You can then ask, well, what if you want to go after sort of lowest lying fruit on the tree, which is the dark photon? And here it's actually the exact opposite, right? Because the dark photon makes vertical transitions that cross the gap almost directly. So this is all driven by the gap. And in this case, you can very literally just go out and measure the photon absorption of quantum dots, which is extremely well characterized, and modify some very small things and plot sensitivity curves for these quantum dots. And we see that pretty conservative amounts of semiconductor can already do quite well compared to these lines, which are the predicted lines for things like these dielectric stacks that are under development right now. We expect to sort of have a finalized version of these two plots in the next few weeks. Okay. So now we go from the realm of quite realistic to really futuristic. And that's what happens if we take our targets and grow them past the nanoscale, right? So if you go from having quantum dots to having milligram scale sensing masses, right? And the reason why that might be interesting is because there's another interesting coincidence, which is that for masses, for semiconducting masses of order microgram to milligram, you're talking about masses that also line up to be roughly the quantum mass. And so one question that we were asked by some collaborators at Purdue was, can we use these mesoscopic masses to detect ultra heavy dark matter? And it seems like most people would say no. And I wanted to say no, but some smart people, Dan Hardy and Gordon Kernayich and friends, put up this paper 2 years ago where they said, well, what if there's not just a vat of these and you're querying them one by one, but if you have an array of them? So they envision something like an array of oscillators, of pendula, where you're querying each one for its motion very carefully. And you're not going to interact the dark matter by bouncing it off one in particular. You're going to allow the dark matter to go through this sparsely instrumented array, and at the point of closest approach to each one of these oscillators, they're going to receive a small impulse. And even though the impulse will be very small on a oscillator by oscillator level, if you were to take a snapshot, what you would realize is that the signal to noise ratio of the track-like signature is actually quite large. And so, the proposal here is fairly futuristic, but the setup, I think, is very clean. So what we're talking about is a 1 cubic meter array of force sensors where the masses are mesoscale, running at a temperature of 10 millikelvin, which isn't too far out of the ordinary, and for sensors that are sort of bleeding edge, but not impossible. And we can ask, what's the signal to noise ratio of these tracks as a very heavy dark matter candidate flies through your detector? And we can write that down pretty readily. And it really just depends on the sensor mass, the dark matter mass, these few parameters, and depending on how you parameterize the interaction between the dark matter and your sensors, a few things pop out. So for purely gravitational coupling, it turns out the mass of the dark matter needs to be about 1 milligram, and the mass of the sensor also about 1 milligram to get very visible tracks. But that was kind of surprising, right? Because that's not terribly impossible, right? And that's kind of the nightmare scenario for dark matter. So the thing that we were approached with was, what other dark matter models can you build that would be visible to such an array? So the obvious thing is like, okay, let's not imagine the nightmare scenario. Let's just imagine some other long-range fifth force. So we parameterize that by changing the potential instead of being GMM over R. It's now also dependent on the masses, but you pull out the charge to mass ratio of both the standard model and dark matter. That's what these lambdas are. And some gauge coupling, right? So like these models are, strictly speaking, non-screened and very long range force. So, bigger than about a centimeter. And already these things are very constrained, right? So the Oshkosh group told us from torsion, pendula, and Weber bars that G has to be less than 10 to the minus 21, which is very constraining. But if you sort of do the math, that also means that the charge to mass ratio of any of these models for the dark matter needs to be greater than like 1200 per GeV, which is a lot, right? Like it's 10 to the 33 per gram in charge. That's a huge amount of charge to stuff into a point-like particle. And also you get a cute thing out of this analysis, which is trying to derive the charge to mass ratio for an undiscrete force in the standard model. It turns out it doesn't really matter the way you parameterize it, as long as you're always saying that you're attaching your mass to the heaviest particle in the visible standard model. You always get that lambda SM is around Avogadro's number. And that's my favorite definition of Avogadro's number, is the charge to mass ratio of the standard model. Okay, so this whole thing
Can
would,
I ask a quick question?
Yeah.
In that experimental setup, like, what were the little floating balls? Are they like these levitating microspheres or?
yeah, so that's
one idea
that's
of
one
it.
example,
Uh-huh.
is the levitating microspheres. You could also imagine things that are essentially microscopic torsion pendula that are coupled to a laser, and you observe these things oscillating back and forth, or nano drum heads.
Okay,
You know, but pretty much any optically coupled
got it.
force
And then-
sensor will do the job.
I don't remember this paper too well, but like you need an array of them.
Yeah,
So one question is like, how big of an array do you need to begin to become interesting? And what's been done now? So like, I know this is very futuristic and that's okay, but like, you need like a billion of these things and
So-
only one or two have been built that been kind of constructed at the same time, or what's the
good.
discrepancy there?
Let me leave the answer to that question for the last slide, because that's
Okay.
the conclusion.
Okay.
But it turns out you need a lot.
Okay.
But it turns out to be not too much to ask, but you do need a lot.
Okay.
In the original proposal, they estimated this, which is like a 1 by 1 by 1 array of sensors separated by about a millimeter. But right now, we're just sort of interested in building models that can be visible here. And the problem all just boils down to confining huge charges to very small volumes. And the more we thought about it, the more we realized that really there's just two classes of models that fit the description. One, a composite dark matter model, because just having one big particle with a huge charge is just not natural. So you have to, you know, if you want your dark matter to be composed of fundamental solutions, particle solutions, then you need to make this a composite state. On the other hand, if your dark matter is not a particle, then you can have something like a non-topological soliton making up your dark sector, and that will confine large amount of charge.
So somehow there's something that's binding it in the dark sector that outdoes the Coulomb repulsion of the accumulated charge.
Well, when I say charge, I mean this fifth force charge. So,
But
you know,
in the
if it's a
end,
scalar
no,
charge,
like,
then it's not
I
repulsive.
was getting, at the very beginning, with your rings of whatever
Uh-huh.
the chemical was, there it was really.
Yeah, there it
sensitive
was.
charge.
Yeah, there it was real electronic charge. Here we're just talking about it. We're envisioning a new fifth force
Uh-huh.
that's going to couple to the standard model. So we're talking about the fifth force charge of the standard model. So if it's a scalar, you know, then that's perfectly fine.
So we said a single particle large charge is not natural. What do you mean?
I mean, you would have to envision a particle that's Planck scale with a charge of 10 to the 33. Right, like that's nice.
Okay, but naturally you just mean the number of sound strands, not any tuning or.
Yeah. I mean, you know, why would the coupling to any gauge be so arbitrarily high? Yeah, okay, yeah, I mean, fine. We wanted to find a better way to
Yeah,
get
just want
to
to
get
know
there.
what you meant by natural.
Yeah. I mean, I can always envision a situation where, like, you know, there's a arbitrarily heavy particle somewhere in the universe with arbitrarily heavy charge, and we're going to look for those, and like, fine, but we wanted to sort of have something that is well motivated to get us to that point. And so that's why we broke it down this way. For this composite dark matter, I think this has been sort of done to death at this point. The parameters involved are just the total charge, mass, and radius of the dark matter. And then inside, what you have is the charge of the constituents, mu, which is the mass energy per particle number, and then the particle number of each state, right? And so things that fall into this category, things like, you know, quark nuggets and dark nuclearites and things of this nature, And it turns out that the charge to mass ratio just really goes as 1 over this mu naught. And since that needs to be greater than 1200 per GeV, it implies that the mass energy per particle number needs to be less than a keV. So your binding energy for your composite model needs to be quite heavy. Otherwise, you'll have, keV scale particles relativistic around Big Bang nucleus of the system. That's no good for anybody. And so the only way this sort of works out is if you have two kinds of forces in your dark sector, one which is long range and one which is confining, very strongly so. And if you ask, where that becomes visible in this parameter space of the total mass versus the mass energy per constituent, it turns out there's no experimental constraints here. It really just comes down to where you expect your gauge coupling to be, and it scales exactly how you would expect. So this is a reasonable way to look for these composite models that sit near the Planck scale. If on the other hand, you don't want to go after particles, but you want to go after some more exotic things, one thing you might think about is cue balls. And what a cue ball is a solution to the field equations where the standing wave is not in real space, but in like internal field space, right? So you have a stationary particle that where the field is rotating in its internal space and creating a radial profile of confined charge due to the symmetry this internal symmetry that it has. And what we did was we made this simplified model of cue balls where there's just two governing equations: how the mass and the radius scale with the charge, right? And there's two limits that are discussed at length in the literature, which are these thick-walled versus thin-walled cue balls. And what that corresponds to is how the radial profile changes, right? So if you have something that looks essentially like a hard sphere, that's a thin-walled cue ball versus something that's much more spread out, kind of like a Gaussian fluffy cue ball. That's a thick-walled cue ball. And the requirements that we made on these models was that they be visible and point-like. In other words, that they leave visible traces in our detector, and that they be point-like because they need to leave a discrete track, not just a fuzzy track. And experimental constraints on these really only exist at these masses from self-interactions, and that's because these things are physically extended. And so we can plot the parameter space that's visible and point-like, and we find that thin-walled cue balls are really kind of ruled out at this point for the most part. And the things that are the parts of parameter space that are visible to a setup of a large array of mechanical sensing oscillators is really quite small. But the thick-walled kind are actually prime candidates to be looked for in this way. And the reason for that is that really just comes down to the way that the radius scales with mass. Not only that, but you could motivate the fact that these things may exist by the fact that they are good SIDM candidates, right? They give you the natural self-interaction that you want at these scales. Okay, what about the gravitational coupling? Well, okay, and this comes back to the question that Asher asked, which is how big an experiment do you need? How do you need to instrument it to have a reasonably high event rate? And what we found is that we need a lot. We need something closer to like a 3 by 3 by 3 array of sensors spaced by about 1 micrometer and exposing for about 5 years. And even though this seems like no way this will never happen, just remember this is the instrumentation density of human skin. So like this is possible in the physical world. It's just a matter of technology catching up.
Wait, sorry, 3 by 3 by 3 is 3 meters by 3 meters?
Yeah.
Thank you. I mean,
Yeah, sorry, yeah. And okay, so yeah, this really implies that we're not close to ever really deploying this in our lifetime, but I think technology being what it is, it's really only a matter of time before we get instrumentation densities that they get to these points. Moreover, there are already 2 experimental groups, one at Purdue and one in the Northeast, that are going after making prototypes of these mechanical sensing arrays not just for these ultra high mass dark matter, but because you can also look for ultralight dark matter by looking at the coherent waves that they generate. And so the example that I want to tell you all about is the Windchime project. So this is led by Dan Carney and Raphael Lang from Purdue. And they're sort of putting together a team to execute a small prototype of these mechanical sensing arrays. And they sort of helped out with this project. I guess we'll take some questions.
Awesome. Questions?
I'm confused about how on shell the first two, the quantum dots and the crystal things,
Sure.
how on shell those proposals are. You have prototype
Yeah.
in the first case.
So, yeah, liquid state molecules already executed, already done, took 6 months from beginning to end. Solid state, we have a sample, we have experimentalists that are involved in it. The crystal is being characterized right now, and presumably there is a space that can be headed for me when that is. So I guess the wheels are moving, and the experimental collaboration is in its early infancy. It's called the axolotl collaboration, but yeah, that will happen eventually. It's too cheap not to happen. You know, these are detectors that can be made with the leftovers from 10-year-old experiments. And the quantum dots, that we're still working on the theory proposal, and hopefully in a year or two those things can be calibrated. But I think the punchline to this is, when you go after these benchtop chemical systems, the time between proposal and deployment is really quite short, because most of these things have been characterized already. You don't need to reinvent the wheel like you had to do with skipper CCDs.
Now, on the Sensei topic, are there any, let's suppose that things are slow for you guys and Sensei rolls ahead. Are there any distinguishing features between the two of the proposals that would be like, well, even though Sensei has reached whatever its level of maturity, we should still do this. Forget about the fact that it's so cheap and you should just do it because it's so cheap, you might as well do it.
Yeah.
But do you get access to theory space or something like that in a way that you don't with Sensei?
You get scalability that you will with Sensei. So Sensei, in some sense, is the best possible thing that can happen to our experiment, because what Sensei is developing is essentially the world's best photo detector. So in an ideal world, Sensei would perfect all of its technology. We would take a skipper CCD and slap it to the side of a large crystal and take data that way. So the more research that Sensei does, and like the more they develop, the better it is for us. And in fact, we've had discussions with Dr. Tippenberg about using some of their old prototypes to run observations with organic crystals.
You mean you just can't have like a huge amount of skipper CCDs?
Yeah.
Okay.
I mean, the biggest proposal for skipper CCD is like order kilograms, right?
Okay. Yeah. Right.
A kilogram of organic scintillator is something you can pick up off the shelf.
Right.
How many individual detectors are in this Windchime? What's the goal?
So I think they're going for either tens or hundreds, depending on what sensing bits they find. But I think what they're really trying to show is that in the prototype, you can do a readout scheme that is not, prohibitive, because really that's the limiting thing. Is like you can't instrument hundreds of billions of sensors, and knowing that that you can't observe tracks. I mean, just the question of how to calibrate one of these arrays is totally non-trivial. Right? There's nothing that you can really produce on Earth that can mimic a grain of sand traveling at 300 kilometers per second through an entire. So all of these things need to be worked out, and that's why the prototype needs to be a very small array, and it needs to be perfect.
Back to the earlier stuff with the simulator and so on. So thinking about it in terms of electromagnetic interaction, it'd be really nice to be able to be sensitive to very light particles that only interacted with hadrons, like with the nucleus. is I can't on live think it through well enough to know. Of course, if you impart momentum to the nucleus, ultimately the whole atom moves. And in your system, would that, have you ever estimated the sensitivity sort of indirectly to non-electromagnetic?
I wish I had someone like you that ever talk like this. Yes, it's exactly what we're thinking about. It is the analog of the Migdal effect for molecules. Hopefully in 2 months, we'll have results from that. That is something we're considering. And the question is, if you deform the molecule very rapidly, does that couple to the electronic states and give you the same photon signal? The answer we're finding is yes. And it turns out there's 2 types of Migdal effects in molecules that, don't have versions in the atomic case, right? So in the atomic case, what you have is an atom, you move the nucleus very quickly, and it, gives off electrons. But in a
Well, it
molecule,
depends on how much energy you transfer, right? If
Yeah.
You're talking about very, very tiny energy transfers, and so all that would happen is the whole atom would move.
yeah. If you want to do the same calculation with molecules, it's a bit more subtle because the molecule is allowed to deform internally, not just move its center of mass. And so you get these 2 effects, and they actually look to be also directional in the same way that the electronic excitations are correctly. And they have complementary selection rules, and I think it's very interesting, and very soon we'll have something out about this. But yeah, that's exactly the next logical thing is like, what happens if you strike a nucleus?
I have a very naive question. So you said the quantum dot has much smaller gap energy than the single molecule. So could you please give me some intuition why
Why that is?
yeah, why that is? Because you mean the larger, I just the formula is
Good.
quantum
So
will R, right? And which means
So-
larger the R is.
So- a quantum dot, the lower bound for the band gap of a quantum dot is really just set by the band gap of the bulk semiconductor. And semiconductors can have arbitrarily low band gaps, which means that take something with a band gap of like, 0.37 eV, like that's sulfide. You can have anything above that by starting to shrink the bulk down to a quantum dot. The more you squeeze the wave function, the more that gap separates.
Oh,
And so that's sort of the knob that we play with.
thank you.
Any question, but I think I answered myself.
Okay.
Right.
So naively, I just think, the inside state, when you open the gap, is because you add some interaction, and open the gap, right? Why you shrink the volume thing and also.
Well, it just comes from the fact that the interaction that you open up is the surface term becomes important, right? Like the surface term in a bulk semiconductor can always be neglected. But here you're making a semiconductor where it's all surface. So you have to take into account the surface interactions.
Then you can effective. Thank you.
Really random question. In the high school, the first science paper I ever worked on was about this only chemistry term I remember. It was about phenylene and phenylene dyes, and they were like these carbon things with these 2 carbon rings, like what you were showing.
Yeah,
But it was even wackier because the idea was to increase their fluorescence by putting other kinds of rings of molecules around
yeah.
the wings so that they're less likely to go into vibrational modes and more likely to go into to fluoresce.
Yep.
Are there crazy molecules that you guys have thought about? Maybe you already mentioned it, just to increase the fluorescence by.
Well, I didn't know I had another chemist. Yes. Yes, you totally do that. If you want to move away from the boring standard molecules, you can add functional groups to do exactly what you said, to try to increase the fluorescence quantum yield. The thing is, with Trans-stilbene, it's already quite high. You can get it up to 90% by functionalizing different parts of it.
Okay.
But then the problem becomes, how much do you perturb the fundamental quantum states in such a way that they're still treatable analytically?
Okay.
Right.
And your number was already starting at 65%.
Yeah.
So it's not a huge change.
But say we want to go lower than that in molecules, and we want to make the molecule a little bit bigger, then you start having to functionalize it. And it turns out one of the ways to do that is to move away from these organic networks of phenyl rings and move to what are called charge transfer complexes, where the transition can be better understood as a charge separation that occurs when you excite, and then the photon gets emitted when it recombines. And that's a sort of like, it's a fancier class of molecules, but it also has a pretty high fluorescence quantity.
Okay, great. Thanks, Carlos. Good.
Very much. That was really fun.
Thank you.
So I'm embarrassed. It does say